We've previously learned how to graph exponential functions. The rest of Chapter 3, we've been dealing with log functions. And we know how to convert them, and we understand that we can go from log form to exponential form. But we also need to graph log forms, or log functions. And just like we had characteristics of exponential functions, we also have characteristics of log functions. And a lot of these characteristics should make sense because understanding that the inverse of a log function is the exponential function, then we should be able to understand that if inverse means we've swapped the x's and y's, with the exponential forms, it had a domain of all real numbers and a range of 0 to infinity. And notice now that has swapped. The domain is now 0 to infinity, and the range is negative infinity to positive infinity. So a lot of these characteristics should make sense because if they're inverses, we've just reversed the x's and the y's. So if domain is x and range is y, we've inverted that. Okay, also with the exponentials, we know that it had a y-intercept of 1. It had the point 0, 1, and these have the point 1, 0. Now, again, just like we were talking about with exponentials, this is only for the form of log base b of x. Okay? The shape of the graph hasn't really changed from the exponential form. If the base is greater than 1, then this is still going to be an increasing function. If your base is between 0 and 1, then it's going to be a decreasing function. Now, that's the same thing. Now, it has a different shape, but it's still the same idea. And instead of having a horizontal asymptote at y equals 0, it has a vertical asymptote at x equals 0. So a lot of similarities, and if you do understand the concept that these are inverses, the log and the exponential are inverses of each other, then a lot of these characteristics will make sense because everything has just swapped around. So look at this explanation of the graph of 2 to the x power and log base 2 of x. Since they are inverses of each other, now we have already graphed 2 to the x power, and these are some of the numbers we plugged in, and that's what we got. And you can see that this is the blue graph here. So we graphed that one a couple times in section 3.1. Now, if I graph log base 2 of x, this is what the numbers would look like. All of the ordered pairs have been reversed. Instead of having the ordered pair -2 and a fourth, we have 1/4 and -2. Instead of having 0, 1, we have 1, 0. Instead of having 1 and 2, we have 2, 1. And again, that's because they're inverses. And then you can see what the shape of the log function looks like. It's still, from left to right, it's increasing. Just like the 2 to the x graph is also increasing. It has a different shape. We can see that instead of crossing through 0, 1, it crosses through 1, 0. And we can see that the domain, this graph now, is bounded from 0 and goes out to infinity. So the domain starts at 0 and goes to infinity. And then we can see that the range now is all real numbers. So all of these characteristics, we can kind of see that and see that the 2 to the x, the exponential, and the log are complete inverses of each other. Everything has been reversed. And that's basically the concept for how we're going to get these graphed. And again, just as a quick refresher, because we're still going to be using transformations, these formulas again have not changed, but to refresh our memory again, if we've got a log function, if we add a number to the end of it, that's going to shift it up. If we subtract a number, it's going to shift it down. If we put a plus c into the log or a minus c into the log, that's going to shift it left and right. The plus shifts it to the left. The minus shifts it to the right. So formulas again haven't changed, but there is just another explanation, another chart for you if you want to keep those handy, print those out, or whatever, to keep that handy. The formulas haven't changed. Alright, so the way, or one of the best ways to approach the logs is, it does tell us here, first graph f of x equals 4 to the x, and graph log base 4 to the x power. Now, previously in section 3.2, we've learned how to go from exponential form to log form, and we also learned that they were equivalent. They were the exact same thing. Well, now we're saying that they're inverses. Now I want you to pay really close attention to this to try to understand. And starting here, say for instance, just going back and looking at example A. This was its exponential form. We said that 12 squared is equal to x. So this is in what we call exponential form. If I convert that into or back into log form, remember all we did was take the base of the exponent and move it over. So this was left with 2 equals the 12 moved over to the other side to become the base of the log, and that's what we have. And we said that this is the same thing as that. Okay? And then the vice versa was true. We said log base 2 of 16. We know that that's the same thing as 2 to the y power equals 16. Okay? So we said these are the exact same thing. And the reason why we have these conversions is because we can't plug that into a calculator and solve that. And we can't solve it as it is, but if we put it into exponential form, we can now see that, well, that's actually equal to 4. So that's what log base 2 of 16 is actually equal to. But we can't do that in a calculator, so we have to get it from log form to exponential form. So before we were saying these were exact equal. We converted out of log form and put it to its equivalent, or the same thing, in exponential form. Now here's the difference. We're saying that these are inverses. They're not equivalent. And let me show you why. We know that f of x equals 4 to the x power is the same thing as y equals 4 to the x power. If I were to take this and put it into its equivalent log form, I want to put it into what it's actually equal to as a log, then, of course, the base of the 4 is going to move over to the other side, so this would actually be log base 4 of y is equal to x. Now, is that the same thing as this? It's not, because this, g of x, this is y equals log base 4 of x. If I just take that out of function form, compare this with this. What's the only thing that you see changed? This is y equals, this is x equals. This has the x here, this has the y here. So are the x and y's not reversed on this? They are. So it can get a little tricky, a little confusing, so we have to really understand our basics of this, that this f of x equals 4 to the x that's given to me is exactly equivalent to this. That would be the same exact thing. However, I'm going to graph this. It's an inverse. Okay, I've swapped. So that's why whatever we get here for this 4 to the x, it's going to be an inverse of that log, and that's why we can graph them as inverses. We're not graphing the equivalent of 4 to the x, we're graphing its inverse. So really important to study that and look at the difference here. Again, to put it into a different form, to just really put this into perspective, let me give you another way to look at this. This is f of x equals 4 to the x power, so this is an exponential form. If I were to take this and put it into exponential form, the 4 would move over, this would be 4 to the y power equals x. Now compare this to y equals 4 to the x power. Let's compare it in exponential form. What do you see that's different? This one has y in the exponent, this has x in the exponent. This one has it equal to y, this one has it equal to x. Again, you can see that these are exact inverses of each other. Okay? So again, what we're being asked to do here is graph a log. The reason why we need to graph the exponential here is because how hard is it to graph this 4 to the x? Well, we know that it's going to go through 0, 1. If I plug me in a couple numbers to the right and a couple numbers to the left, it's fairly basic to do this. We plug in 1 for x, which gives me 4. When we plug in 2 for x, it gives me 16. When we plug in the -1, that gives me 1 over 4, the inverse, which we talked about in the first section when we learned how to graph these. And plugging in the -2 gives me 1 over 4 squared, which will give me the inverse of what I got for +2. Now, that's pretty simple. That's pretty simple arithmetic to be able to do that. If I just ask you to graph this log and we try to set up a chart and plug in numbers and do the exact same thing, how difficult would that be? I'd have to plug in y equals log base 4 of 1. I can't plug that in my calculator. We learned that earlier in the section, which means every single time I plug in a number here, I'm going to have to plug it into the log. I'm going to have to convert it into exponential form, and so that would be, okay, 4 to the y power equals 1. So I got to figure out 4 to what power gives me 1. So that would be kind of simple. I'd have to do the same thing for 2. I'd have to do the same thing for -1, -2, and that's a lot of work. That gets a lot, pretty complicated. And so what if I said, well, okay, well, we know that this is the same thing as 4 to the y power equals x. So if I plug in 2, I have 4 to the y power equals 2. Well, 4 to what power gives me 2? I can't do that. That's not an even number. So then I'm stuck. Okay? So it's a lot more difficult to just graph a log by plugging in numbers, because we can't just plug it in our calculator. We've got to convert it into exponential form, and then we're not guaranteed that we're going to get a number that we can actually work with. So the whole point of this is graph the exponentials like we know how, and since we now know and understand that these are just inverses of each other, for me to be able to graph this log here, all I have to do is reverse all the order pairs. If this one has -2 and 1 over 16, then this one has 1 over 16 and -2. This one will be 1/4 and -1, 1 and 0, 4 and 1, and 16 and 2. That's why we have to understand that these are inverses. That's why we have to graph starting with the exponential, and then once we have the exponential, the rest of it is just reverse your order pairs. So 1 and 4, 2 and 16. It's going to go off my graph a little bit. -1 and 1/4, -2 and 1 over 16. So here's my graph of, this one is 4 to the x power. And graphing now my log would be, this time 1 and 0, 4 and 1. Again, 16 and 2 is going to go off my graph a little bit. 1/4 and -1 means I'm going to go over about 1/4 and down to -1, and then over 1/16 and down to 2. And you can see, based on what we already know these graphs are supposed to look like, we now have the log graphed. So the idea of graphing the log, again, I can't really stress this enough, is you can't just graph the log. You can, but it's pretty complicated. We could turn that into an exponent, but the x's and the y's are opposite of what we're used to for plugging stuff in. And we may end up with numbers that are off our graph, or end up with numbers that we can't solve. So the easiest thing to do is graph the inverse of what we have. Instead of graphing this, we're going to graph 4 to the x equals y. Just change that out so we can plug in the numbers easily, and then just reverse everything that we have. Okay, so again, if I did ask you for the domain, because of the characteristics that we already know, the domain here is going to be 0 to infinity, and the range would be -infinity to +infinity. So taking that idea just a little bit further, there will be times that you're asked just for the domain of the log function. And you're not even necessarily asked to graph it, but we just want to know what the domain of that log function is. So to kind of understand that, first of all, if we understand the transformations, that will help us understand how the domain is going to move. We did do that in section 3.1 when we graphed just the exponentials and we graphed their transformations. We looked at how the domain and the domain didn't change, but on that one the range did change. Now, it says here, with the log functions, it reverses the domain and the range of the exponential. The domain of log functions, if it's in that form, is the set of all positive real numbers. And you can kind of read through this, but what we're going to try to get down to and understand is if we have a transformation, the domain we can find just by looking at the function is going to consist of all the x's for which your g of x, whatever's behind your log, here. So for instance, if you look down at example 7, just that x plus 3, we take that, we set it greater than 0, and that's going to tell me how my domain has moved. Since this is the set of all positive real numbers, meaning it doesn't include negatives, it starts at 0 and goes to infinity, so that's what we already knew. To find that transformation, all we have to do is take the transformation part and set it greater than 0 and find out how that's going to move. So I'm going to show you two ways to work this one. Understanding your transformations is very helpful on this one. So if I start just by using transformations, using the logic side of this, if I take my log base 4 of x, which is what we just graphed in this last example, we know that this red graph is the graph of log base 4 of x. If I am just putting in a plus 3 here, first of all, I'm putting it into the log since it's inside the parentheses, which means it is going to shift it left or right. Since it's a positive 3, the transformation is left 3. Just using that idea of transformations, if I look at this red graph, if I took all of these order pairs and shift it to the left 3, see 1, 2, 3, it's all these points are just going to shift over to the left 3. Guess what's going to happen to my domain? It's going to move from 0 to negative 3. So that's one way we can do it. That's how much and how often your transformations can come in handy and can save you a little bit of time. Or you can use this definition that we just went through about the domain of a log function means take the g of x part. So take what's behind your log, take that x plus 3, and set it greater than 0. That's what that's telling me to do here, and solve it. When I subtract my 3 over to the other side, my domain should be every x that's greater than negative 3, which is as an interval. Everything greater than negative 3 is going to, obviously, to the right. Greater than is to the right, going to the positive side. So just kind of take that stuff into consideration. There are other ways of looking at things. There's other ways of looking at domain and graphing these functions. Transformations can really come in handy if you have a visual and you know those formulas.